Okay, so let's try to play the game with the Tower of Hanoi toy. So remember the rules of the game. We start with all the discs on the first peg, and we want to end up as in a second picture. And at every move, we could take a disc and put it on a different peg as long as that different peg has either nothing or the top disc on it is bigger than the disc that we are moving. So how many steps do we need to move Tower of 8 or in general n discs? So let's call the number of moves needed to transfer all the discs needed to get to our goal h of n. Here h just stands for Hanoi. And by the way, this number of moves really doesn't take into account whether you're moving something from peg number 1 to peg number 2 or from peg number 2 to peg number 3 or any other way. It will be the same number of steps, just from one peg to another peg, provided originally there is a tower on the peg you are starting with. Let's call it first, and you end up with the whole tower in the right order on your goal peg. Let's call it second. So first of all, if you would only have one peg, it would take us just one step to transfer it. You pick it up, you move it, there is nothing to do because the second peg is empty, so you could just do it. So here is the interesting part. Suppose that you already transferred, say, n-1, all but one of the disk onto a different peg. And again, we really don't care which peg it will be. So how do we now end up with transferring that last disk? So we are going from configuration when we have the biggest disk on the first peg, let's say, the tower except for the biggest disk on the third peg, and we want to move the whole tower on peg number 2. Well, in this case, you'll need to move the disk from peg 1 to peg 2 and move the whole tower. So if you have the whole tower with n disk on peg 1, then you could kind of do it in 3 stages. First, you move n-1 pegs to peg 3, and that will take h of n-1 steps. Then we'll put the remaining disk to peg 2, 1 step, and then we will move the disk from the third to the second peg, creating a tower. And for that, again, we need that h of n-1 steps. So you see, it kind of reminds you of the induction that we just did. We sort of assume that we already know how to move n-1 disks. And from that knowledge, we figure out how to move n disks. That's exactly the same kind of reasoning. But rather than doing a proof, here we end up with a formula. So we can compute the value of h of n by taking 2 times the value of h at n-1 and adding 1 to it. That 2 here comes from needing to move the tower of n-1 first from peg 1 to peg 3 and then from peg 3 to peg 2, and the 1 is moving the biggest disk. So I gave you the recurrence. I didn't really tell you yet how many steps it takes. So let's do that now. So let's compute the answer for n equals 8. So we know that h of 8 is 2 times h of 7 plus 1. Good, but not good enough. But we know that h of 7 is 2 times h of 6 plus 1. Now we got a formula that we could simplify. It will be 4 times h of 6 plus 3. Now we just keep going and going and going. H of 6 is 2 times h of 5 plus 1. Then we do h of 5, h of 4, h of 3, h of 2. And finally we end up with 128 times h of 1 plus 127. Well, h of 1 is just equal to 1. So it will be 128 plus 127, and that's 255. So 255 moves will take you a while to do, but eventually you could solve the puzzle this way. So can you get the answer directly without having to go through all the intermediate steps, computing h of 7, h of 6, h of 5, and so on and so forth? You can if you can figure out the so-called closed form of a recurrence, which, well, kind of makes it not a recurrence, it just makes it a formula that directly tells you the value of h of n in terms of just n. It doesn't reference h of anything else that comes before. Well, it may reference, and usually does, the initial value, but essentially it expresses the value of whatever you're computing, h of n, in terms of just the initial value and the number n. So the closed form of the Tower of Hanoi recurrence, as we will see in a moment, is 2 to the n minus 1. And indeed, if you compute 2 to the 8 minus 1, it will be 256 minus 1, 255. Finding a closed form is often called solving a recurrence, because well, this is something that can give you an answer right away for any value of n. So here's how we could solve the recurrence. We notice a pattern, we write a formula, then we prove that this formula works by induction. So you could notice the pattern like this. First time when we applied the recurrent rule, we got 2 times h of n minus 1 plus 1. Second time we got 2 times 2 times h of n minus 2 plus 2 and plus 1. If you do it one more time, you get 2 to the power of 3, 2 times 2 times 2 times h of n minus 3 plus 2 to 2 squared plus 2 plus 1. Again, you're probably seeing the pattern. It's 2 to the power of what you subtracted from n plus the list of all the powers of 2 that come before whatever 2 to the 4 in this case. So generally, you could compute this as a sum from I equals 0 to n minus 1 of the powers of 2. 2 to the 0 will be 1, 2 to the 1 will be 2, so it will be 1 plus 2 plus 4 plus 8 plus and so on and so forth. And actually we could show that this sum has a very nice form. It's 2 to the n minus 1. So actually let's quickly do this just as a kind of on the back of a napkin exercise and induction. Why would it be 2 to the n minus 1? And in general, why would this sum have this value? So we start with the sum from 0 to 0 of 2 to the I being, well, 2 to the 0, that's 1. That's our base case. Let's now assume that h of k and the sum from I equals 0 to k minus 1 of 2 to the I equals 2 to the k minus 1. That's induction hypothesis. And for the induction step, we just use a recurrence. So we say that h of k plus 1 will be 2 times h of k plus 1. But we assume that we know what h of k is. This is 2 to the k minus 1. You stick it into a formula, you get exactly the answer you wanted. If you know binary numbers, there is actually an easier proof of this statement. If you think of a binary number that consists only of ones, and you add 1 to it, you end up with a number that's a power of 2. It has only one 1, followed by a bunch of zeros. Which means that if you take a power of 2 and subtract 1, you get a binary number with all ones corresponding to 2 to the n minus 1 plus 2 to the n minus 2, and so on and so forth up to 2 to the 0.